In this series, I will be talking about the inner mechanics of a neural network training. I will be sharing the way that I study this subject, how I look into the problem to comprehend it better. At first, I will work on a simplified version of the problem. Then step by step, we will grow our model into a fully developed deep neural network. I will also implement each step. At the end, we will have a fully developed neural network implementation in our hands. It may require some math background to follow up with me, but I will not dive into the details of the equations that much. I will be more focused on the graphical visualizations in the training process. My purpose is to have a picture of how things work under the hood in a training process. Now, if we make a quick dive into the subject, with an AI model, we take some input, evaluate these input in our model, and produce some output. We can make these evaluations with a fixed algorithm specific to a purpose. In this type of approach, this model doesn't benefit from machine learning. In such a case, it is limited with the intelligence of the algorithm designer. The most common type of machine learning is something called supervised learning. It's also like the entry point of these topics. In supervised learning, you have some initial dataset. This dataset is something like questions with answers. There are input information and also output information. You use this dataset for training your model. And neural networks are the most commonly used tools today for training machine learning models. A neural network is like a chunk of parameters, weights, that you process your input data with, and it produces an output or multiple outputs. At first, those weights are initialized randomly, so your model don't know anything, it produces silly outputs. But for the initial dataset, you have also the answer, so you know how wrong you are when you give an answer. And there comes the heart of the problem. If you can find the relationship between the error you produce and the weights within your neural network, then you can refine the parameters of your network in a way that will decrease the error amount. And this is called neural network training. You repeat these refinement steps many times, again and again, and then you try to get close to the expected value as much as possible. After you complete your training with the initial data, you release your model to the real world now. In the real world, you give some inputs, the inputs that you don't know the answer to, and your network will produce some answers with the trained weights. A neural network is like a complicated function, and in the training process you train the parameters of this complicated function. Now let me explain things on a simple scenario. Think that this is our initial dataset. The horizontal axis represents the input and the vertical axis is the output. This dataset has a single input and single output. In different scenarios it can have multiple inputs and multiple outputs. You can think these two values as the size of an house and the price of an house. So we have such an information and we try to devise a model that will predict the price of an house based on its size. At first we will use a line as our prediction model. So what does this mean, using a line as a prediction model? When you ask your line model, how much does a 100 square meter house cost? It says it's cost something around 7,000. The line is a simple function with simple parameters. So the result of the line function at a given specific point is the answer of our model. We can query this model in any way we want, at any point. The input data, the blue points here, have limited information at some specified points. They don't give any other information. But by using a prediction model, we can query any point at the input axis. For example, you can query the price of a 200 square meter house, and this your model can give you an answer. So that's why we want to create a prediction model. Now let's turn back to our initial case. We have a prediction line with random initial parameters, and currently the results that our model produces is a little bit far from the expected value. Here, this is the point from our initial dataset. So the expected result at this given input is something like 95. You see there is some difference between the expected result and our prediction model's answer. And now we will try to move our prediction line closer to this point by updating the parameters of the line. Function of a line is this. The first parameter is the slope, and the second parameter is something like an offset value. It is the intersection point with the y-axis. I will simplify this thing a little bit further, and I will use this function for our prediction model. Now what I'm trying to do is to understand the problem in its most simplistic form, so I will work on a line function that passes through the origin. I will also change these two letters. P is for prediction model, and W is the short for weight parameters in a neural network. This is just for convenience, it's something unimportant. At first we will start working on a single point. This means that in our initial dataset we have only one sample data, and its input is 2 and its output is 3. We want our prediction line to give the same answer. Currently, when it is just initialized with random weights before training, it gives 2 as the answer. This model is very simple, it has only one weight parameter. We will move this prediction line to the desired values by adjusting this single parameter. Here the problem is that when this parameter has an initial random value, how will we know the direction to update this parameter to get closer to expected value? At this point we will use the error we made. Error is a metric that increases as we get further from this point and decreases as we get closer. It doesn't need to be the exact amount between the expected value and our predicted value. So now we will devise an error function in terms of W. This function is also called loss function or cost function many times, and the global convention for naming this function is J. Now we will write this function in terms of W. If we simply take the difference between the predicted value and the expected result, this expression becomes positive when our line is one side of the expected value, but it will be negative on the other side. But we want it to increase in both directions. So I will take the square of this expression. Taking the absolute value would also work, but this is more common and have some benefits. Now this function is something that will increase as we move further from the expected values. It works on both sides. Now we wrote this expression for only a single point in our simple scenario. This one is the value of our prediction, and this is the expected result. I'll write this part in terms of W. It's Wx. In this case, x is 2. Our input is 2 here. Now we have a loss function at hand. To see this on this graph, I will change the name of this parameter to x, but don't confuse this with the input value we use for prediction function. This function is on a completely different context. So in this green function, the horizontal line is W parameter, and the vertical line is the error value, loss, cost. These are all used interchangeably. We now have a relationship between W and our loss function. Our aim is to find a W that minimizes the loss. In this very simple scenario, it's easy to calculate analytically, but we want to find a more generic solution that will work on different scenarios. Trying each possibility for real-valued parameters are not an option in most of the cases in terms of processing power, as you can guess. So we need a smarter approach. Now for any given value of W, we will try to find the direction that will decrease this function, the error. For example, in our case, the initial value of W is 1. You can think of it like we dropped a ball at this point, and by the help of gravity, the ball will try to reach to the lowest point of this graph. So when the value of W is 1, we will increase it to reach the minimum loss value. We can say this because we see the slope on the graph. The mathematical expression of the slope is called derivative. So in mathematical terms, the thing we're going to do is to change this W parameter in the negative direction of this derivative at this point. So let's write it now. We will update W in the negative direction of the derivative of the cost function with respect to W. This derivative expression gives us the direction. So to determine the step size, we also use something called the learning rate. This is just a constant to determine the size of the step. I will give it something like 0.1 for now. Now let's calculate this. W is equal to 1 minus derivative of this expression is, first we take the outer part, then we take the derivative of the inner side. This is constant, and the derivative of this part is 2. Here by x we mean W actually, and its initial value is 1. So the result of this expression is, it seems, minus 4. This will be, the new value of W will be 0.4. It means that on the graph, in just a single step, it will jump to this point, from here to here. For a step size, this seems a little bit big. We may decrease the step size just to be more precise. So we can use smaller learning rates for this. Okay, now let's implement these in code. We will make the implementations in Python. We will only use NumPy as a library. We will not use any machine learning library. We will write everything from scratch. We will not work on one big project. We will make separate implementations for smaller problems at first, and in time, as the problems get complicated, our code base will turn into a fully developed deep neural network implementation. And now for our first problem, we have a single data point, and its input is 2 and its expected value is 3. Our prediction model has a single parameter, and its initial value is, let's say, 1. Learning rate. Now the predicted value of our prediction model is this. With this at hand, our error value is at first it must be 1 if I remember correctly. Yeah. Now let's find derivative, then update our parameter, and then check the error again. Okay, the updated parameter is 1.4 as we calculated. The error is okay. Now let's recap this step on the graphics. At first, our W parameter was 1, so you are here, and after the first step, W parameter became 1.4. So we jumped from this point to this point. In this example, we were lucky. Although this step size is a little bit large, it landed on somewhere close to optimum value. If this step size becomes too large, it's also possible that it may deviate from the optimum result at each step. So it's more preferable to use smaller steps. while trying to get close to the optimal point. Here I will mention a detail. It may be a little bit confusing for some, but don't worry if you can't comprehend it at first. It doesn't affect the overall picture. In our example, if the size of the first step were larger than 1, then it would land on somewhere here. This is a convex graph, so after this point, the magnitude of the slope of the equation is larger than the magnitude of the slope at this point. The magnitude of the slope, the derivative, is the second factor that affects the size of a step, in addition to learning rate. So what this means is that at each step, the size of the jump will increase. So that's why your model will deviate from the desired result at each step. On the other hand, when it is smaller than 1, at each step the size of the jump will get smaller, which means that you can get close to the desired point more precisely. This is something that makes convex functions as desirable loss functions in many cases. Here, instead of the squared error function we used, if we use the absolute error function, which is the absolute difference between our predicted value and the target value, our function would be something like this. So as we get closer to the minimum point, our step size wouldn't change. Now I will decrease the learning rate. This time W became 1.04 in a single step. So it's something around here. This is the step now. To get somewhere close to this point, we need to take multiple steps. So we will keep repeating these steps until we get somewhere close enough to this location. And to decide whether we have reached somewhere close enough, we will use a threshold, error threshold. This technique we have been using is called gradient descent, and it is a numeric method. It's not an analytical solution. In an analytical solution, you calculate the exact result in a single step, whereas in numeric methods, you try to make guesses about the solution and then measure whether your guess is close enough to the solution. So that's why we define an error threshold here. After each step, we measure the error, and if it's less than a small threshold we defined, we say that that result is good enough for me. These two lines here is the step that we will keep repeating. In the first one, we calculate the derivative, and in the second one, we update our parameter with it. So we will keep repeating these steps as long as the error is larger than 0.1. This is our threshold. By the way, this is not the only option to decide when to stop training. You can use different criteria. If the training takes too long, you may want to end it after a certain amount of steps, or you may want to stop training if the error stops decreasing further, even though it's not very close to zero yet. There is an ideal environment in our simple scenario, but in real-world problems, because of different reasons, there is usually noise in the training data you work with. The error function is likely to converge before getting close to zero in many cases. Okay, let's first check this from the graph. Here the vertical axis is the error. We put our threshold here. It's 0.1. It means that our code will keep updating the W and take these steps until it reaches somewhere below this point. Now let's run this code. 1.34. So it stopped taking steps when W reached somewhere around here. Now if we want to get closer, we can decrease this threshold. It is 145. And now it's even closer. The exact value is 1.5 here. Now let's tidy things up a little bit. I will call the error as cost. In neural network frameworks, you will frequently encounter a word called gradient. It's just a fancy name for derivative. In this example, we worked with a single point, but normally we will work with multiple points. So passing x as an argument to these methods is better. You can keep using these methods with slight modifications in other examples. This thing we have done here is the core of the concept of model training. After now, we will mostly deal with the same things in higher dimensions. We will deal with multiple inputs in our initial dataset, and also each input sample can have multiple dimensions. The weights of our prediction model will also be in multiple dimensions. In addition to increasing dimensions, there is only one subject called activation, and after that we will have covered the whole deep neural network training topic. Also at the end we will have a fully developed deep neural network training code at our hand. In the next lesson we will work with training with multiple samples.